Okay, welcome to a new talk in the virtual seminar of Geometry with Symmetries. It's a great pleasure to introduce Nazia Valiyakath from Syracuse University. She will talk about nilpotent and solvable quasi-Einstein manifolds. Thank you, Nazia.
Thank you so much for the introduction and thank you for the invitation. Um, I'm Nazia. I am a PhD student at Syracuse University. My advisor is Will Wiley at SU. I'm going to talk about nilpotent and solvable quasi-Einstein manifolds. So this work, I did this work as part of my PhD thesis, and I'm still working on some problems in this area. Um, let me start with some motivation. So, a smooth manifolds can admit infinitely many different Riemannian metrics. So we can ask the question, what is the best metric for to put on a given manifold? Now, what do we mean by best metric? So one example is Einstein metric. Um, so metric is Einstein metric if Ricci curvature equals lambda times g. G is the metric. If this happens, then we say that the manifold is an Einstein manifold and the metric is an Einstein metric. Also, a similar best metric is Ricci-Soliton metric. So a metric is Ricci-Soliton if Ricci curvature plus half LXG. So X is a vector field of the manifold, and LXG is the Lie derivative. So Lie derivative of the metric with respect to vector field X. So if this equals lambda times G, then we say that the metric is Ricci-Soliton. So these are some examples of this best metrics that we are talking about. Now, a motivation to study quasi-Einstein metric, one motivation is that this theorem by Doty that says on non-flat unimodular solvable Lie groups, they do not admit an Einstein metric. So unimodular means every Lie group comes with a Harmesher. So if the Harmesher is left and right invariant, then the Lie group is called unimodular. Or for computation and for more practical purpose, we can use this equivalent definition of unimodularity when we take the vector field in the Lie algebra of the Lie group. And if for every element in the Lie algebra, if trace of adjoint operator is 0, then it's called unimodular. Adjoint operator is just taking the Lie bracket. That's adjoint operator. So if trace of that is 0, then it's unimodular. And solvable Lie group means this following series terminates. So we have this theorem by Doty on solvable Lie groups. So we can ask the question, if it does not admit Einstein metric, how close is it to admitting an Einstein metric? Do they admit a quasi-Einstein metric? So let me tell you what a quasi-Einstein metric is. So here is the definition. A Riemannian manifold is called quasi-Einstein, or it admits quasi-Einstein metric if the Ricci plus half of the Lie derivative with respect to the vector field X minus 1 over m. M can be any non-zero real number. X star tensor X star. So when this equals lambda G, X star is this evaluation map. So you can see that this almost looks like a Ricci-Soliton, but with this extra term. Now, we denote such a triplet as M, which is a manifold, G is the vector, and X the vector field. And we will refer to this lambda as quasi-Einstein constant. Okay, so now why does this metric look like this? Why do we study this? So as you can see, when the vector field is 0, then the equation is just Einstein equation. And when m goes to infinity, the equation reduces to Ricci-Soliton equation. And when m equals to 2, this is where this metric actually originated from. The solutions to this equation are called near horizon geometries. So these are, this is a topic in black hole theory. So yeah, this is another motivation for this metric. And if our vector field is a gradient vector field, then we can write the quasi-Einstein equation in this form as a special case. So there has been several studies about quasi-Einstein metric, like when is this about this vector field X, whether it's killing or not killing. So let me talk about some classification results, because since what I'm working on is the classification. So Barros, Ribeiro, and Filho give a complete description of quasi-Einstein metrics on three-dimensional homogeneous manifolds with isometry group of dimension 4. Chen-Liang Zhu proved that every compact simple Lie group admits non-trivial quasi-Einstein metrics except these three groups. And Lafuente and Peterson and Wiley also studied gradient M quasi-Einstein metrics. So yeah, gradient solutions on non-compact homogeneous spaces. And then Alice Lim, she was a student of my advisor, Will Wiley. She classified the compact locally homogeneous non-gradient M quasi-Einstein 3 manifolds. Now, about this vector field X in quasi-Einstein triplet MGX. So in the result of Chen-Liang Zhu, so there's this result when they studied compact Lie groups. If G is a compact Lie group with a left-invariant metric G, and if it is quasi-Einstein, then they proved that the vector field X is left invariant and killing vector field. So killing vector field means the Lie derivative term is 0. Also, another similar result by Alice Lim is that if G is unimodular Lie group with left invariant metric G, and if the triplet is quasi-Einstein, also if X is left invariant, then X is a killing field. Also, all known examples of M quasi-Einstein manifolds, so far that we know, have the X in the M quasi-Einstein equation left invariant. So this kind of leads us to assuming that X is left invariant in the equation. But let me just tell you one more theorem that will also motivated us to assume that X is left invariant. So this is this theorem that I proved. So this is general for any Lie group with co-compact lattice gamma, not just for solvable, for any Lie group. So if we have, let's take pi to be the covering map from G to the quotient, then let's take a metric on the quotient such that its pullback is left invariant. Then we get that the triplet, the quotient is M quasi-Einstein, if and only if the group itself is M quasi-Einstein, where this pullback vector field external with respect to which the group is M quasi-Einstein is left invariant and killing. So this this also motivates us to assuming that X is a left invariant vector field. We do not have an equivalent theorem for, let's say, in like Ricci-Soliton case. In Ricci-Soliton, the X doesn't have to be left invariant or anything. So this is the reason why I'm going to assume that X is left invariant. And so I define such matrices, such metrics as totally left invariant quasi-Einstein. So quasi-Einstein metric such that the metric is left invariant and the vector field is left invariant. We will call it to be totally left invariant quasi-Einstein. Like we don't know if these two notions are equivalent on a non-compact manifold. Yeah, so but when we assume that X is left invariant, we have some benefits. So the previous theorem by Alice Lim that I said, which says if G is unimodular and if it is totally left invariant quasi-Einstein. So I'm going to denote totally left invariant quasi-Einstein by TLQE. Then she proved that X is killer, right? And what I'm studying is unimodular solvable Lie group currently. So I can assume that the X with respect to which it is totally left invariant quasi-Einstein is killing. So that means instead of looking at solutions for this equation here, we just have to look for solutions for this equation, like one less term to worry about. Okay. Now, so now that we have the new equation or like simplified equation, let's look at quasi-Einstein metric on unimodular solvable Lie group. So first thing that we prove is if the unimodular solvable Lie group is if it admits totally left invariant quasi-Einstein, then the quasi-Einstein constant lambda is 0 if and only if the group is flat. So only in the flat case. So how about when it is non-flat? So when it's non-flat, unimodular solvable Lie group with totally left invariant quasi-Einstein metric has the X lies in the center, and the S, the Lie group S, has to be one-dimensional center, has to have one-dimensional center. So this theorem, since it's for any unimodular solvable Lie group, we know that nilpotent Lie groups are unimodular solvable Lie group. So it's kind of easy to see in the nilpotent case. For in this unimodular solvable case, like it's a slightly longer proof. But if you consider, let's say we have ngx, and if n is nilpotent, and this is if this admits totally left invariant quasi-Einstein. Oh, we don't have to, yeah, okay. Total left invariant quasi-Einstein. Then by Lim's results, we can use that X is killing, right? So we have that X is killing. Now, so it's a killing vector field on nilpotent Lie algebra. And so that means the Lie derivative of X with respect to Lie derivative of G with respect to X. So since G is left invariant metric and X is left invariant vector field, we can say that LXG is ADX plus transpose of adjoint operator. And then since x is scaling, this has to be 0. And so that means ADX is adjoint operator is skew symmetric. But n is nilpotent. So ADX is nilpotent operator. But then the operator is skew symmetric and nilpotent. That happens if and only if ADX is 0. So that tells us that X is in the center of the Lie algebra of N.
Nazia, may
Yeah.
I ask you?
Yeah.
So in your setting, let's say in the end, you are studying Riemannian metrics with
Yeah.
two Ricci eigenvalues, only two. One of
Yeah.
them multiplicity 1.
Yes.
That would be the
Yeah, exactly. Yeah.
condition, right?
Yeah, exactly. So that's what I
Equivalent
wrote
to
here.
that?
Yeah.
Okay.
Yeah.
Thank you.
Yeah. So yeah, exactly. So we get that the Ricci curvature has two eigenvalues because of this theorem that X has to be in the center. And then the quasi-Einstein constant lambda, we also obtain that the lambda is negative. And this two eigenvalues, so one in the direction of center. So let me just write it down. Let's say Z spans the center. Then so we will have that Ricci of center is positive and Ricci in the other direction, like okay, sorry, it's better to use X because I started with X. Ricci of X is positive, and anything that is perpendicular to X that has Ricci equals lambda and less than 0. So that's what we are currently looking at. Now,
But I mean, this is in general when X is killing, not only
yeah.
in this case, right? Okay.
When X is this is when X is killing when unimodular solvable. So we don't know about non-unimodular. It doesn't have to be.
No, but I mean from the general definition of quasi-Einstein. If X is killing, then you are only saying that there are two Ricci eigenvalues, one of
Yeah.
them of multiplicity 1, right?
Yeah, that is true. Yeah, that is true.
Okay,
Yeah.
okay.
Yeah.
I was confused. Thanks.
Okay. Okay. So now that we have this for all unimodular solvable Lie groups, we can say that we can say some things about nilpotent case. So any solvable Lie algebra can be written as S equals A plus N, where N is the nilradical, maximal nilpotent ideal. And then yeah, so it's nilpotent Lie algebras. These are a subclass of solvable Lie algebras. So the first example of nilpotent Lie groups that I want to talk about is the Heisenberg Lie groups. So that's when Heisenberg Lie group is Heisenberg Lie group is upper triangular matrices with one on the diagonal, and so here A is a raw vector and B is a column vector and I is the identity. So the Lie algebra, so it has a very simple Lie algebra structure. Lie algebra is spanned by this Z. If Z is the center, then we can say that this is the basis of the Lie algebra. And this xi comma yj, the brackets goes to Z, and it's 0 if I not equals j, and every other Lie brackets are 0. So I'm talking about Heisenberg because in three-dimensional case, by the result of Alice Lim, we have that Heisenberg is the unique unimodular solvable Lie group that admits quasi-Einstein metric, and so it's natural to suspect what happens in the higher dimension, whether it's just Heisenberg or if there are more examples. Now, turns out that in higher dimension, even in higher dimension, non-abelian nilpotent Lie group admits totally left-invariant quasi-Einstein metric if and only if it is isomorphic to a Heisenberg Lie group. And such metric on Heisenberg is unique up to isometry and scaling. So to prove that Heisenberg admits such a metric, as we just said, it's not really difficult because we just have to compute Ricci curvature in the center direction, and that will be positive, and in the other direction we will have that it's negative. And if we take the nil-soliton metric, then in the other direction the Ricci curvature will be equal. So it's actually same as the nil-soliton metric, and that's what gives us the isometry and uniqueness up to isometry and scaling. But in the other direction, like to say that that's the only example, so I just put the Ricci formula here so that we can use it. So I'll just tell you an idea about why are these the only example. So having this one-dimensional center. So there's this lemma by Kirillov. So I think Kirillov proved it for like things in representation theory of nilpotent Lie groups. So if n is a nilpotent Lie algebra with one-dimensional center, and if it's Z that spans the one-dimensional center, then Kirillov says that there exists a vector space decomposition for n. It's just a vector space decomposition, not a Lie algebra decomposition, as Rx plus Ry plus Rz plus W. It's kind of like a leftover. And then this brackets in X and Y goes to Z. And brackets of Y with anything in W is 0. And we also know that this subspace is an ideal of the nilradical, ideal of the nilpotent Lie algebra. So so this means if we can say that if ngx is totally left-invariant quasi-Einstein, so first thing that we can prove is since it has one-dimensional center, we can apply Kirillov lemma, and it admits, I'll call this basis by Kirillov as Kirillov basis. It admits a Kirillov basis that is also orthonormal. Because we kind of need orthonormal basis to compute. So even like this Ricci formula, it's when you have an orthonormal basis, like here E, K, and EJs are orthonormal. So yeah, so we can say that it admits a Kirillov basis that is orthonormal. Now we have that Ricci. So since it's totally left-invariant quasi-Einstein, so this implies that Ricci of x comma x, this equals Ricci of y comma y, and Ricci of FD, other basis vectors in W. So we know that this equals the quasi-Einstein constant lambda, and except for the Ricci in Z direction, which is the center. So this will be something positive. So once we have this restriction, we can write down the Ricci formula, and then what we get is that we get a bit more insight into the underlying Lie algebra structure. So it tells us that it's not just, so we have xy equals z from the Kirillov lemma, and yw is 0. So not just yw is 0, the brackets of x with w is also 0. That's what we get when we put this Ricci formula restrictions. And we get a little bit more than this condition here. Ry plus Rz plus W is an ideal. So we get that, in fact, Rz plus W is an ideal of the Lie algebra of N. Okay, so once we get this, what we do is we use induction on the dimension of N. So since we have these details about the Lie algebra structure, we can prove that if we take a basis, if we take the Kirillov basis, W1, etc., up to WS, this subalgebra that is constructed by Z and WIs, so that subalgebra is totally left-invariant quasi-Einstein, like Z plus W is TLQE. So we will get this, and by the induction hypothesis that is Heisenberg, so then we can prove that the nilpotent, the whole nilpotent Lie algebra is isomorphic to Heisenberg Lie algebra. So that's the structure of the proof. Now we can also ask if we can construct compact manifolds that admit quasi-Einstein metric out of these examples that we know, the Heisenberg ones. So we call something a nilmanifold, a manifold a nilmanifold if it is a nilpotent Lie group quotiented by its lattice. Now we have lattice for Heisenberg. The integer subgroup forms a lattice for Heisenberg Lie group. So we also have the theorem that the first theorem that I talked about that we proved is if we have the quotient M quasi-Einstein, if and only if, that happens if and only if the group itself is totally left-invariant quasi-Einstein. So in this case, we can take Heisenberg, and then we know that Heisenberg is totally left-invariant quasi-Einstein. So its quotient by this lattice is admits M quasi-Einstein metric. Okay, so as a corollary, we can say in the language of the black hole theory, we can say that the only near horizon geometries on a nilmanifold are Hn mod gamma. Hn is the Heisenberg Lie group when n greater than or equal to 3. Near horizon geometry, as we said, it is the 2 quasi-Einstein when m equals 2. Case. Okay. So that's what I have to say about the nilpotent case. Now, going back to unimodular solvable.
Sorry,
group,
Nazia.
Yeah.
Do you hear me?
Yeah,
Sorry, I had a problem with the audio. in this last slide,
Mhm.
you're saying that for any m, I'm interested in the constant m. Is this positive, negative, or you take it arbitrary, or you restrict it
Oh,
to imply the TLQE condition?
for this theorem, right?
Yes.
Yeah, this theorem is true for any m.
For any m.
Yeah.
Okay, and the TLQE condition doesn't have any the parameter m. Does it enter on the equation?
That has m2. Yeah, that has m2. But like all the example that I construct, like we can keep varying m. Yeah, about m, I didn't actually say anything about m. Like since in the nilpotent case, since we have lambda is less than 0, that's going to imply that m is positive.
Okay.
In nilpotent. Yeah.
But in general solvable, do you get negative m's?
In unimodular solvable, we get it's all negative. In the non-unimodular, we don't know. Yeah.
Okay.
If we can get positive.
Thank you.
Mm-hmm. Okay. So yeah, moving to unimodular solvable Lie group, can we say anything more about the structure? Yes, turns out that we can say something, but then I have with an assumption on the Lie algebra structure. So I'm going to assume that the adjoint operator is normal. So let me tell you about that. So S is solvable. That means, as I said, it's A plus N. Now, if I take any A in the non-nilradical part, then the adjoint operator acts on the nilradical part, also on the other vectors. So this is ADA, the adjoint operator. Now ADA is normal. That means ADA normal means ADA commutes with its transpose. Okay, so I'm assuming this, and in that case, if S is non-flat and it's unimodular, solvable, and if it admits a quasi-Einstein metric, then this happens if and only if the following 4 conditions are satisfied. The nilradical has to be totally left-invariant quasi-Einstein with the same quasi-Einstein constant lambda. So that just says n is Heisenberg, actually, because we know that Heisenberg is the only totally left-invariant quasi-Einstein. And the non-nilradical part, the brackets are 0. So that says this is just Euclidean. Now, the center of S is exactly the center of N. So that says center of S, if I denote it with Z of S, is one-dimensional spanned by the X in the quasi-Einstein. And then the 4th condition is just a restriction so that we have the correct quasi-Einstein constant lambda. So this
so in this theorem you need add A to be normal with respect to G.
Yes, with respect to G. Yeah.
Okay. Thanks.
Yeah, to see this, so this theorem, it looks pretty similar to the structure theorem for Ritchie-Soliton on solvable Lie groups, except that I guess in that case, in Ritchie-Soliton case, you can prove that adjoint operator is always normal if it's Ritchie-Soliton. So we cannot do it here. But yeah, other than that, this condition looks kind of similar. And the proof, it's kind of easy to see in at least in one direction. If we look at the Ricci formula for unimodular solvable Lie groups, so this is what it looks like. This A's are from the non-nilradical part, and the X is from the nilradical. So let's look at the Ricci curvature of Ricci formula for elements in nilradical. If we have a adjoint operator is normal, that means it commutes with the transpose, so this term actually goes away. And so I'm proving in this direction. If these four conditions are satisfied, it is totally left-invariant quasi-Einstein. And if it's standard, this term goes away. So we are left with Ricci curvature of nilradical. So this is just Ricci curvature of nilradical. And if we know that the nilradical is totally left-invariant quasi-Einstein, then this is this lambda g plus 1 over m x star tensor x star. Okay. So we have that, and so in the nilradical part we are good, and in the non-nilradical part we know that it's standard, so this term goes away, and then we put the fourth restriction so that this equals lambda g of a comma a. Yeah, so the fourth condition takes care of that. And there's non-diagonal Ricci terms, so this term goes away because it's standard. The brackets are 0 in the non-nilradical part, and since we assume that adjoint operator is normal, it is not very difficult to prove that the remaining term is 0. So we have Ricci curvature. We have the Ricci curvatures equal in n-1 direction, and negative and positive in the other direction. So it is quasi-Einstein, totally left-invariant quasi-Einstein. Now, okay, so we have a very good idea about the Lie algebra structure when ad A is normal in the quasi-Einstein condition. We know that the non-nilradical part is Euclidean and the nilradical part is Heisenberg. And what about the brackets of A with N? So we can say the structure of adjoint operator up to isometry. We can say that it is diagonal, and these are the diagonal elements, and it has to add up to 0 because we are still talking about unimodular case. Yeah, so we can, given any dimension, we can say what are the unimodular solvable Lie groups with ad A normal and totally left-invariant that admit totally left-invariant quasi-Einstein metric. So I just put here the classification up to 7 dimension. We can go on like this. We can just make examples, Heisenberg, and add Euclidean part. Yeah, so here in these examples are nilpotent. These are not nilpotent. Yeah. Now, things that we haven't answered is definitely about vector field X, whether it has to be left invariant always, That is a question that we do not have an answer for. But the question 2 and 3, if it's unimodular, does adjoint operator always have to be normal? Also, what happens when the solvable Lie group is non-unimodular? So we have some answers. So in my current work with Roberto Araujo, we explored, we're still looking at it, examples that are of the form one-dimensional extensions of nilpotent Lie groups. So this can be normal, this can be, the D depends on D, whether it's normal or not. Also, it can be solvable, it can be unimodular, it can be non-unimodular. And we obtained an example that admit totally left-invariant quasi-Einstein metric and is unimodular, solvable, but D is not normal. So this is such an example. The D we made D looks like it's D cannot be any metrics. Yeah, we put restrictions so that it is not normal, and that admits quasi-Einstein metric. Also, about whether X has to be killing, it turns out that it does not have to be killing when it does not have to be always killing. So if X belongs to the nilradical, then X is killing. So this is happening in the unimodular case. And if X is not in the nilradical, then X is not killing, and the nilradical is an algebraic Ricci soliton. So that's all we know, at least in one-dimensional extension. Yeah, so this is slightly more general, the one-dimensional extension, because we haven't put any restrictions like unimodular or non-unimodular. But these are still one-dimensional extensions. We don't know much beyond that. Yeah, that's it. That's all I have to talk about. And thank you, everyone.
Thank you very much, Nazia, for the very nice talk. Are there more questions?
I have a question. When you have the uniqueness of the Lie algebra in these cases with nilpotent and solvable unimodular, is the metric, if you specify M, is the metric determined, or?
If you specify M, like so that goes to the scaling factor. So
Okay.
it's unique up to isometry and scaling. So it's the same metric up to isometry and
okay.
scaling. Yeah.
Mhm. I was also curious your result about the vector field having to be left-invariant. Is there, I don't know, I assume that's probably too complicated to summarize what goes into that. That seems like a really nice result.
So I do not have, so here it's only in the compact case, right? Yeah, I guess
Yeah.
this is the theorem that you're talking about.
Yeah,
it's
that's really nice.
thank you. So we use this theorem by Cochrane that says on compact manifolds with a constant scalar curvature. So with constant scalar curvature, if it's M quasi-Einstein, then he proved that X is killing. So if I use this, I have that G mod gamma is compact with constant scalar curvature. So I have that X is killing. So since it's if it's M quasi-Einstein, then I know that X is it's an eigenvector of the Ricci curvature. And the left invariance of X comes from the Ricci eigenspace being left invariant. Yeah, that's what goes into the proof.
Oh, okay. Thank
Mainly.
you. Yeah, really
Thank you.
interesting.
So, Nazia, can I make a comment about
Yeah.
this?
Yeah, sure.
Which might be interesting to people is that I think we tried, and you tried to give a proof of this that was Lie theoretic, but this proof is not like algebraic. This result was proven by Eric Cochran, who's another one of my students, and the proof doesn't involve homogeneous geometry at all. It's a divergence theorem integrating these kinds of Bachner type theorems on the manifold. So it'd be very interesting, I think, to have a proof of this theorem that's just Lie theoretic, right? And we couldn't come up with one. So
Okay, are there more questions or comments? Okay, if not, we thank Nazia again. Thank you very much, Nazia.
Thank you everyone for attending.
Thank you. It was a really, really beautiful talk.